Hello and welcome back to Aerospace and Mechanical Lab 2. Today we are going to talk about fourth lab of Lab 2 series, which is the composite manufacturing through the VARTM method. So the idea for the manufacturing lab is for you to study the flow through a porous media using glass fiber. In this lab we use glass fiber, not the carbon fiber, by conducting vacuum-assisted resin transfusion or transfer molding. And eventually at the end of this lab, you are going to characterize the effective permeability and fabric permeability of the glass fiber. Essentially, you are going to calculate it. And eventually at the end, you always might need to do a statistical analysis, right? One thing you have to keep in mind is while you're doing this experiment, you have to record the video of resin front moving on your fiber. Make sure to watch the video of lab recording and make sure to work with your TA to understand what to do for this specific lab. So we are going to introduce what composites are today, and we're going to talk about applications of composites, where they are used, move on to different methods of composite manufacturing, and eventually we are going to formulate the flow through porous media, which is the flow of resin through the fiber and the guiding medium that we have here. So composite materials are usually made from two or more layers of any fiber. It can be glass fiber, carbon fiber, or any type of fiber. And then you put these layers up to on top of each other and add resin to the whole system. You let the resin cure, and you are going to have your composite plate, composite panel, composite material in general. But why do we choose composites instead of metals or any other types of material? There are a couple of very important reasons. One is the composite materials are much lighter compared to metals, while they retain their high specific stiffness and high specific strength. So light materials that are stiff and strong. That is the main reason we choose composites. And the reason they are very strong is because the fibers in the direction of fiber can be stronger than the metal. And another important point about composites is that we can engineer them to have the desired modulus of elasticity based on the pattern of your fiber. You can see different examples of composite materials right here, and we can see the modulus of elasticity can change very, very much. And it also does change in different directions as well. Like whereas steel and aluminum, for example, are going to have the same modulus of elasticity no matter what, unless you heat treat them or strain harden or whatever. Like the material itself is going to have retain the same modulus of elasticity, right? Well, where do we use composites? Composites are basically used everywhere. Like in a plane, nowadays 50% of a plane is made up of composites. The same is true for the wind tunnels. There are some cars, like the car you see here, this BMW i3, that are completely made of composites, right? These are very important for new types of car, electric vehicles as well, because in electric vehicles the weight is a very important factor. Composites have a very wide use in biomedical applications as well. As you can see here, this prosthetic is made by composite, and also the components inside the cars and planes and everything else that are also used. So composites are made of two things: fibers and resin. We need to understand the fibers a little better. The fibers can be very high strength when they are attached to the matrix. And we have different types of fibers. As I said, we can have glass fibers and carbon fibers, different types of fibers. The patterns we can make with these fibers are different. We can have a biaxial weave, triaxial weave, knits, or different types of layering. We can essentially change the strength of composites by the different patterns we use in building our composite plane, and there is no limit in how you can actually put your fibers on top of each other. And then other than the pattern of each layer, as I said, the way you put different layers on top of each other can actually change the strength of the material as well. Like the fiber you make, the layers, complete layers, is called the preform. After you add the resin, depending on the resin you have added, you can have two different types of composites. Your composite can be in the same line as thermoplastic or thermosets. The difference between the two is thermoplastic can be melted and reshaped repeatedly, but thermosets cannot be melted. And the type of material we use, the type of epoxy we use, the type of composite plate we are going to make in the lab is going to be in the thermoset, essentially behave like a thermoset. The difference between the two starts from before their application. Thermoplastics are solid at room temperature. You need to melt them down. Thermosets are liquid at room temperature. Thermoplastic need heat to liquefy. Thermosets need heat to catalyze and start curing. And we're going to see that in the lab, or a hardener. As we said earlier in the previous slides, thermoplastics are remeltable and recyclable, whereas the thermosets, when you cure them, you won't be able to liquefy them. Thermoplastics have a high viscosity at processing temperatures, whereas the thermosets have a low viscosity at processing temperatures. We have different types of composite manufacturing processes, but all of them have a curing or some sort of a curing involved. So essentially have to let the resin cure and harden. Before the curing process, we need to make sure all of the air pockets are removed from our composite panel. In the VARTM process that we're going to use, that is done through creating a vacuum. Okay. Let's actually move on to different types of composite manufacturing processes. The three that we are going to talk about here are called the wet hand layup. The second one is called the resin transfer molding, RTM. And the last one is called the vacuum assisted resin transfer molding, or VARTM, which is the type of the manufacturing process we use. There's an example of a composite manufactured car is a solar car. Most of the solar cars are manufactured using composites. The reason is the weight here is of the utmost importance. Okay. So wet hand layup is the simplest type of composite making. You essentially create a mold and you pour resin in your mold. Then you place the fabric on top of resin. You press the fabric with a handheld roller, and then you, after you've made sure that your fiber has been impregnated by the resin, you add the next layer and repeat until you are done adding all of the layer. You essentially let it cure in an oven or exposed to air, direct atmospheric conditions. And the quality of this usually depends on the operator's skill. This is a very labor intensive process. Resin transfer molding has taken this process up a little bit. Essentially, you have to cut your preform, you have to stack your preform first. We haven't added any resin to this whole thing. And then you compact your fiber, right? When you compact your fiber, you are going to add resin to your system, and then the resin can actually go out from these outlets. right? And then we let it cure and then remove the mold. This is how you get to do the resin transfer molding. Now the problem with the resin transfer molding is the air pockets. Right? The only thing that we are using here to remove the air pockets is the mold itself, right? So to avoid this problem, we have created a VARTM process. The VARTM process essentially you create a hole in your sealant to the vacuum pump, and you create a hole for your inlet. You essentially are going to suck air in through your panel and suck air out. This way, you are going to make sure that there are no air pockets left in your composite panel. One thing you need to make sure for this specific process is that you need to make sure that your seal is perfect, so you can actually remove all of the air bubbles, air pockets from your system. There's a step-by-step process here. You have to cut your preform, you have to stack your preform, and there is a distribution media that you want to make sure you put on your composites. The reason we add the distribution media is because we want to make sure that we actually have a uniform resin throughout our whole system. And we do the bagging and sealing, vacuum, and impregnation by infusion, and eventually demolding. So this whole process, except for the preform cutting, will be done by you in the lab, as you have seen in the video. If we have a video of a VARTM process, this is essentially the last step of it. This is for a boat, and this is where we are infusing the resin. This is the distribution media, the green one, and you can see how the resin has been distributed throughout the whole system. Okay. So whenever you do the VARTM process, you want to make sure that you have your fiber is fully covered by resin. There are no dry spots. And you have a fast process cycle, right? All of these are related to the permeability of the system. Essentially, how much the resin can fill all of the spots in your fiber. This depends on the resin itself, also depends on the fiber. So we need to bring both of these into account to do the calculations. To do our calculations, we need to understand, have a little bit of understanding about flow-through porous media. Based on the Darcy's laws, the flow rate Q through the porous media depends on the permeability in the X direction, which is K, the cross-sectional area, which is this cross-section, right? Flow is passing through this whole thing, this whole fiber, and the pressure gradient in our system, pressure gradient is the vacuum pressure, which is 0 minus the atmospheric pressure. So pressure gradient is 0 minus the atmospheric pressure. And the viscosity of the fluid itself, which will be given to you, and then the velocity here is the volume average Darcy velocity. So there are a couple of assumptions we are making here. One assumption, again, if you go watch the lab video, we are going to have a better understanding of this, is that one of the assumptions we are making is the flow front here that is moving in this direction is moving uniformly. So flow front, there is no curved flow front, essentially. It is moving as a line, which is obviously not correct, but it will give us a good understanding of the permeability with a very low degree of error. So that's one-dimensional flow assumption. That is the main assumption we are making here. That is how we can actually convert the flow rate to cross-sectional area multiplied by the velocity. But this is not the equation you want to use. So if you simplify the equation, again, the flow front, this is your fiber, this is your resin. We are going to assume that the flow front is moving as a line, one-dimensional flow rate. If you simplify the equation, eventually you are going to get to this relationship, which is the relationship between the location of the flow front from the center of the coordinate system, which is where your fibers are located, begin essentially. We can relate this to the time that has passed. And the relationship is essentially x squared, which is the location squared, is equal to 2 multiplied by your permeability multiplied by the inlet pressure, which in your case is your atmospheric pressure, 1 atmosphere, divided by the viscosity, divided by the porosity, phi, right? Okay, multiplied by porosity. So essentially, your goal in the lab would be to create the composite material and then track the location using your own phone, track the location of the front of the resin with respect to time. Then you plug this in here. We have the pressure, we have the viscosity. You're going to be given the viscosity. You can calculate the porosity. And this n here shouldn't be this. There is no power of n. I make sure that this is corrected in your slides. You essentially plug this n, plug all these values in. You will be able to calculate the permeability of your composites. Okay, and eventually, for each location and each time, you are going to be given us a graph that looks like this. So at each time, you're going to calculate a flow front location. You are going to be having a flow front location, and based on this, you can calculate the effective permeability, right? So again, you take your data, you create this graph, and then you find the slope of the graph, which when multiplied by the porosity and divided by the pressure is going to give us the effective permeability of composite. And you can do the statistical analysis using Excel where you are doing the graph. This is going to give you the regression coefficient. The statistical analysis for this lab is not as important as the other labs for us. We want to make sure you actually learn how to create a composite panel, and we want to make sure you actually learn how to use Excel for this, for your graphing. There are a couple of calculations you need to do before finalizing your permeability calculations. You need to calculate the effective porosity of the material, which is essentially the porosity, a weighted average of the porosity of the guiding medium that we put on the fibers and the fibers themselves. These are the height of the guiding medium, distribution media, and height of the fiber. The total height here, it is a weighted average. There is nothing more to it. The effective thickness, essentially the thickness of the two added to each other, and the porosity of fiber, essentially 1 minus volume of the fiber. This is how we calculate the volume of the fiber. This is the areal weight that is again given to you. Number of the fabric layers, you can do 2, 4, 6, or 8. We don't really, the number of layers you use is not that important to us. We want to make sure you actually know the number of layers and do calculations based on those number of layers. And the porosity of this distribution medium can also be calculated using the same formulation, y minus the volume fraction of the distribution medium. Same ideas. So to do these calculations, you're going to need numbers from this table. Right? Everything you need in this table is given to you. Right? You want to keep in mind that the areal weight specifically is the areal weight of a single. Here, I'm sorry, I need to fix this, but this is the areal weight of 6 or 8 layers of fabric. So if you're doing 2 or 4 layers, you have to divide this number by 6 and then multiply it by 2. Okay, your TAs are going to be helping you. So this table essentially is the table you need to fill in a lab report. This is what we are going to need from you. You need to answer in your, worksheet. You need to answer all of these questions. You need to calculate all of this. You need to measure all of these in the lab. And you need to give us this graph and answer all of the questions. That is all you need to do for this lab. Please let us know if you have any questions, and thank you for listening.